Right. Okay, so without further ado, we'll get into the session this morning. Seeing we're running a little bit late, what we're going to do is cut out question time completely, so we'll run all the way through till 11:20.
You have a handheld. Okay.
Hello, good morning.
So we're going to stand about here, by the way, for the purposes of light. Okay. Welcome. This is Matt Evans.
This is Rusty Russell.
Did you like that? We practiced that.
And today we're going to
talk about how Unix grew up. But before we get into that, Matt's going to humour me here. I always start my talks these days with a slide showing you stuff that means that if you get nothing else out of it, at least you'll have 3 cool projects that I introduced to you in the first 30 seconds of the talk to remember. The first one is called Spark. It's on GitHub. It's a shell script that's a command line sparkline generator. Uses Unicode to generate these. So if you are back in the 70s,
my RxVT didn't work. URxVT, the
so you can type
Unicode
Spark 1, 2, 3, 4, 5, 6, and it gives you a little thing like that on the command line. Very, very cool. Second project is Plover, an open source stenography alternative, which is very much a proprietary, locked down kind of area that most of us don't experience. And so I've actually gone directly and put the donate page there, hint, hint, for that project. And
a Cray 1A in an FPGA. It rhymes. But it's quite a cool hack as well.
Yeah, if you like your retro computing. And even better, he's actually built a Cray 1 style case about this big to hold the FPGA in it.
So all he needs now is an operating system. So if anyone happens to have that lying around, get in touch.
Check that out.
The year was 1976. The hair was long, the shoes were tall.
Rusty, can you move your microphone across to the other side?
Okay.
Then we can hear it better.
Cool. Just some mic issues.
This is a PDP-11 pictured. I'm not sure if this was the fully kitted out one. They, I think, were 2 megabytes, or 1 mega word, 16-bit words, fully kitted out. There's a couple of disk packs, some
Yep, is that mic better?
And so forth.
Good? Okay. Yes. Now, unfortunately, as you can see, it's a multi-user machine because there's 2 teletypes in front of it. We don't have, unfortunately, a PDP-11 here with us today. Should have asked. Thank you, Bidal. Luckily, we don't have one. So the closest thing that we can get is this. So here we go. At least it's green.
See how fast it boots?
Yeah, look at that. And it looks pretty much like you'd expect. So there you go. This is pretty much Unix. Right. So all good. We will flip back. Now, we are going to be comparing the PDP-11 running V6 Unix. So this is the one documented in the Lions book, for those of you who have a copy of that, against a modern Unix.
Okay, maybe something else. Maybe desktop Unix.
Yeah, not that one, actually. We're going to compare it against the latest 64-bit x86 Ubuntu. So you can see a kind of a before and after here. Now, we saw before that here are our on-disk binary sizes for cat, grep, and ls. And these are going to be our 3 punching bags through the whole talk.
Because bigger is better.
And here they are today.
Cat is 313 times better.
Yes, ls has clearly got 21 times better than it used to be.
grep 68 times better there.
Yes. Now, the interesting thing is, of course, Unix in the good old days, like today, came with source. So we can...
No, not CD. CD came afterwards. Was it V7 that CD came in? Okay.
Yes, okay. Although I actually edited the shell source on here, so I've got CD if I need it, because I kept getting it wrong.
Tearing all the hair out.
But I'm trying to be genuine here. Now, this feels a little bit recursive, but if we cut the cat sauce, oh, that's interesting.
That's why I'm
Okay, so yes, the first surprise looking into this was, yes, cat is written in assembler. So, okay. We've taken a snippet of the assembler code and what it looks like here. The PDP-11 had a lot of, dereference this, like load from this register and increment the register pre and post and stuff like that. So this is the code that does the command line argument processing. So it pops off the stack into R0, then looks at the first character of R0. Is it a dash? So does that compare?
Remember this compare?
Yes, this compare is important.
Later, the compare
Remember that can be there. Now, if it's not equal to dash, then it jumps 2 forward, so it jumps that 2 label there. Otherwise, it clears the fin location. So fin being the effectively the variable in which we hold the input file descriptor. So it clears it, so it's file descriptor 0, standard in.
There's something weird going on with the syscall there.
Yes. So in V6, arguments to system calls were inline in the text. So immediately after the trap, the sysopen, came the arguments to open. So you modified the code itself to create the open call. So here, we move R0 into 0F, which is the 0 label forward, which we can see here. There's the 0 colon. And so basically this line here writes into there. So it's open. The value of R0 is written to there, and a 0 flag to say read only, of course. So, and if it fails, it jumps out, otherwise it continues. So this is an example of what life was like. And you'll notice, of course, that, has anyone spotted the bug in here?
Race condition?
Race condition, no. No.
It's not 64-bit safe, I'll say.
Okay, yeah. No, it doesn't check for an alternator, so any file that starts with a dash, it will treat as standard input, which I can prove to you. But yes. Oh, sorry. Let's skip forward. Okay, so our previous measurement of just looking at it on disk size is a little bit naive. We're going to get a little tiny bit more sophisticated and add in the BSS. The BSS is the zeroed out data that basically isn't represented on disk, but as soon as you load it into memory, it gets populated. The size command will give you that. So here is how we're going to be representing cat. So we have our text down the bottom. We have our data and BSS, in this case, 2 512-byte buffers, and the fin 2-byte variable. And up the top is the overhead, which this is a.out. And a.out had 8 words, 16 bytes at the head. And that was the only real overhead that we have. Now, we can compare this.
How does this compare?
Using this technique against Ubuntu on the right.
A little sliver down the end.
It looks like this. Okay.
Okay. Well, one of the things that first notice, on the left we've got a very memory-constrained machine. We've got a 2 meg machine compared to a multi-gigabyte Ubuntu machine.
Read the prop, Matt.
Well, it's not a fair comparison.
yes. Thank you.
They've obviously tried to make things very small. They've written it in assembler because of this memory limitation.
Well, actually, no. Interestingly, they haven't. Because if you look through the assembler, they actually jump over one of the system calls. They weren't writing it because they were trying to make it tiny. They were writing it in assembler because it was simply easy. I mean, you're an operating system programmer. You could write an assembler on C, and you can see this. They switch back and forth almost arbitrarily. Certainly when C was very young, a lot of this stuff was written in assembler. You can tell because there's a final flush where it flushes the output buffer. And they actually branch around it if there's nothing in the output buffer. If you're worried about space, you just make the system call anyway. It's a write 0, it's useless. So
they wasted a couple of bytes there.
It gives you a hint that they're just writing the way you would write, not really squeezed.
But that's not fair. Come on, we've got C on one side and assembler on the other.
It is true. It is true. Okay. So what I did is I re-implemented a bug-compatible version of V6 cat. So the same thing.
Which is twice as big.
Well, it is almost twice as big. It's about 80% larger.
But not big enough.
In C. So I re-implemented it in C. Same thing. No error messages, a kind of a pseudo-random exit status, as you saw when I catted a file that didn't exist. Dash, anything starting with dash must be standard in, that kind of thing. And that's what I ended up with. So yeah, we did get a little bit bigger. But there's still a long way to go. Now we can do the same thing for grep and ls. They're already in C, so we don't have to do any porting there. So this is the comparison of Ubuntu versus V6 Unix. Okay, and if we total them together, there we go, that's the sum. And this time you can actually see the one on the left. So there is some text there.
But again, we're going from a small machine to a big machine. You're at least considering that you're not unrolling loops and doing all sorts of stuff. We're compiling O2 on the right.
Right.
So
okay.
Let's compile OS.
Right, yeah, we didn't have that option.
We're going to be much smaller if we did that.
There were 2 options for compiling back in the day. There was optimization or don't. Now obviously we have OS, so we can compile Here's the total with size. But we can make our first relatively definitive statement here, and that is that 30%, we pay a 30% bloat penalty. Consciously, because we chose size over speed. We kind of went, well, speed over size. We went, no, make it fast.
So it's
don't care
slower?
about it.
With OS, there's a performance change.
Ah, good question. Okay, so if we take a directory of 500,000 files and we do an ls, with our standard utilities running, obviously they've compiled with O2, we get numbers out like this. If we compile it with OS, yeah, ls itself doesn't change very much at all, but ls to shell, yeah, we pay about a 9% penalty for speed.
Okay. So 30% for 10% gain-ish.
Yeah, and so someone in the audience, I'm sure, is dying right now to rebuild their entire distribution with OS.
Gentoo people, surely, come on, it'll be one command. One command. Just
And get some more stats and see whether we're actually getting what we pay for with O2.
So we thought one of the other interesting things to talk about would be a nice fuzzy metric. How much of these binaries, we've seen they're very small binaries, but they surely must be very efficient. There's not a lot of waste in there, not a lot of overhead. Get an idea of the coverage of those. How much of that's ever run or accessed? Just as a comparison.
So another exercise.
So it'd be nice if we could do this.
Yeah, somebody out there who's hardcore would be to measure how much of this is actually executed somehow, rather than just doing running size commands and the lazy stuff that we did. And over a set of standard usage scenarios, that'd be awesome.
It would be. So we did. There's a nice emulator called AP Out. I did. Okay. Yeah. There are lots of system emulators, so the PDP-11 will run the full OS and then you'll run the user binaries under that, but a nice emulator called AP Out, which just runs the user binaries. So it's got a PDP-11 interpreter. It will go through, it will hit a PDP-11 V6 syscall. It will then translate that straight through and map it to, open to Linux open and write to open, to write and so forth. But this makes it quite easy to examine just one binary at a time. So you can run the binary in a certain set of switches, certain usage scenario, stick a bitmap somewhere else in memory, because we've only got a 64K address space here, and then set a bit for every byte that's accessed there. So get an idea of exactly how much is used when you run this binary. Write them out and then run a few different things and union all those data sets. And here's what we find. So we saw the cat was tiny, 136 bytes. Almost all of those 136 bytes are used when we open a file, open a non-existent file, read standard in, try and use a standard set of options, use all the options on ls, grep for something that matches, grep for something that doesn't. So this is how our test scenario. So cat, we found they're all of the bytes are accessed, one of them isn't. Do you remember the compare byte instruction when we were showing you the assembler before? Okay, so all the instructions are 16 bits or 32 bits, I think. I don't think they're 40. They're multiples of 16 bits. So the compare byte instruction's got a 16-bit space for its immediate. It's a compare byte instruction, so it only compares the bottom byte of that. So by nature, in the instruction set, there's already a sign of waste.
Bloat
one
everywhere.
byte is wasted, designed into this instruction. Can
What
never
were they
be
thinking? What's interesting is if we jump forward even 3 years to version 7, we can already see cat is now written in C. Also, we've got standard I/O, which we didn't have in V6, and we can already see, our numbers are already dropping precipitously.
LS has almost doubled in size.
Yeah, LS has almost doubled already. So we're already on this sort of downhill slope, even at that point. But getting back to cat, here is our comparison. Now, on your side, things aren't fair either, though, because that, of course, is a shared library.
Everyone uses shared libraries. That's just how you do it.
You're dynamically linking. Yeah, but if we want to do a fair comparison, obviously we didn't have shared libraries. Everything was static back in the day, so...
I'm not sure this is a good idea. I've got a feeling how this is going to go, though. Okay.
You can see the slightly anti-alias.
It's still on the graph there, just so,
V6.
yeah. Okay. So that's huge. It's a massive, massive binary. So, well, why? So we've got almost 700K of stuff, and then the cat itself. It calls printf. It's got help. Maybe there's internationalization there. Maybe it's printing date formats. Who knows? So there's a lot of dependencies, a lot of things that are obviously used in libc there. So my first step was to try and cut it down. I had a very simple program. Return 42 from main. Statically compiled, that's also about 500K. So what the hell is this doing? So just the act of calling main depends on all this other stuff in libc. So there's obviously some startup code involved, and that's always how I thought about it, some startup code. But we had a bit of a dig into it. So there's 17% of libc is brought in as a dependency. There's almost 1,500 .o objects. I did check LD still, I mean, LD doesn't include .os from a .a if you don't use them. And I did have to double check this when I first found, hang on, 500K cannot be needing all of that. But it's underbar start. So libc start main is the first thing that's run. That sets up all sorts of stuff. TLS, it will set up your FPU control word just in case you're returning 42.1. It will do TLS in case you're doing threaded, return 42. You can DL open so that you can have plugins to return the value of different values. So you might have to initialize the dynamic linker and stuff as well. So to have a little bit of a visualization, I draw a graph of the dependencies of libc start main. Up there in the corner, that's libc start main. So there are 313 objects it depends on in libc. So we're going to go through them one by one. Computer, zoom. Okay, so here's a cut-down graph. The red stuff at the edges, I know this is kind of hard to read, but just to give an idea. The stuff at the edges means etc. I've cut down the recursion depth of the dependencies there. So we've got libc start calls main, but then it also calls exit after that. You've got an implicit exit. Exit, you've got at-exit handlers. When you give an at-exit handler, it's malloc. So of course, exit will call the at-exit handlers and then free them, because you don't want to leak memory just as you're exiting. But there's all sorts of odd little dependencies like that. If you are a setuid return 42 program, then you have to check environment variables to make sure that nothing untoward's going on. The very security checks, you will stat the file descriptors and make sure they're not pointing to anything strange so that you can't break into any of this.
Okay. So it's bloated. That's fair enough. But yeah, how much of this is actually run? I mean, sure, it's all there, but how much of it is actually executed?
Well, it would be nice if we could do the same trick as we did on the PDP-11.
But how would we do that,
on x86? Well, we'll need some way of interpreting x86 and running that on x86. And we chose Qemu. So there's the system emulation mode, which people are all familiar with. There's also the user emulation mode, which does the same sort of trick as the AP out PDP-11 emulator. So it will run just a binary. It will translate the syscalls and interpret or translate the code to run it. So in this case, I took Qemu configured in x86 running on x86 configuration, which doesn't sound too useful, but because it's a dynamic code generator and you can then instrument the code that it's generating, you can generate the code so that you do a load or a store, but you also tick something off in a bitmap somewhere. You can do the same trick. So you can see exactly which bytes a particular program accesses of its binary. So that 500K return 42 program, what do we guess? Yep.
Yeah.
Very, very little of it is ever actually run.
Or put another way, we pay about 5,300% penalty for stuff that we never use. So, but okay, yeah. Look, shared glibc is sitting over 1.7 meg and everything else. But I log into an Ubuntu system by default. I've already got 110 processes running that are linked against libc. So you could sanely say we can divide that number by 110 and come out with say that they're only paying 17K each. Or another way, look at all the things that are installed on the system that are dynamically linked against libc, and then you're over about 2,000 binaries. So by that measure, it's actually a very, very small penalty. You're looking at 300, 400 bytes each.
Well, it's tempting to say that, and that's really what we tell ourselves, and that's why we have gone with ELF and shared libraries and so forth for the past few decades, a couple of decades. But, okay. In looking through this, your statically linked LS, that was, I don't recall, 700K, 800K, something of that sort of size. Only about 90K of that's ever accessed. If we do it dynamically linked, this is just as it would be on a normal system. In this case, this was a Debian 6 LS I was looking at. There's 200K of stuff from the LS binary and associated libraries. This is the same code. Okay, so it's this GNU LS on both sides. It's GNU libc, one statically linked and one not. So you're accessing almost twice as much stuff just because you have the privilege of doing it dynamically. So you're trawling through simple tables and you're actually bothering to do the symbol lookup at runtime and link all that stuff up. So another thing that was interesting, so we had 7% of libc being accessed by dynamic LS.
So it pulls in 90K. I mean, that's not too bad.
Okay, so maybe other things will use the rest of it, we hope.
Yeah.
Okay?
But 90K, that's not too bad.
But so the argument, right? You access a page. Okay, well that's cool. I've got a huge, 100 megabyte Emacs binary, say. You're only going to pull in from disk. You're going to demand page in exactly what's used. But the usage patterns are quite spread out. So that 90K is spread out over pages such that 476K, as you can see, is brought in. And I found that the average use was actually really tiny. So for 4K page size, something like 1,1800 bytes on average was used. So
Okay. So LS isn't using it all, but I mean, across the whole system, everything else is going to be using. I mean, you need to do some kind of measurement across the whole system to see what's happening.
Okay. Let's do that. So I tried to fake up a whole system, my average day's work sort of thing. It was quite hard running a lot of things through the user mode QEMU stuff. Some of the syscall mapping isn't done, and it's a bit annoying. I did get a few things running through, and I tried to run a few shells, do some SSH sessions, extern, Opera, Emacs, a couple of browsers there, you see. Emacs is quite good, actually. Almost all of the Emacs binary gets used, or at least a large proportion. I'll say 2/3. To me, that's almost all compared to some of the figures we've just seen. So I ran all these things and took as an amalgam all of the stats that we got from the system binaries, your libcs, your librts, your libp threads, and so forth. So remember, I was looking for pages that were brought in and only a little bit accessed. WebKit was great. So this wasn't the worst one, so whoever's a WebKit developer, I'm not singling you out, but 8.5 megs is read in, only 5 megabytes of that is used, so only 3.5 of that is ever actually accessed. So system-wide, there were 33 megs of actual real wasted RAM, stuff that was brought in from disk and never accessed by anything at all.
Yeah, but I mean, how
on my multi-gigabyte system.
Hey, how can you get too upset about that on like a 4 gig plus laptop?
Okay, well, I've tried to, and I found a way to get upset about this. And my way is this. Okay, so memory is fine. You can get your data set and spread it around and use all these extra pages, and you've got 4 gigs lying around to do this. But you don't have an infinite number of TLB entries. And if your working set is spread across lots of TLB entries, you're going to get TLB pressure. So I wouldn't mind betting real money, maybe actual coins rather than paper money, but I wouldn't mind betting there's a performance impact on this. If you actually had your data squished into maybe a fewer number of pages, or your data and code in this case, I wouldn't mind betting that as well as memory, you'd save some cycles as well. So any keen people in the audience, this would be a really interesting research project. If someone wants to make an ELF reordinator that will take one of these profiles and say, well, this bit's used and that bit's used and not that bit in the middle, and squish it all together, this might be quite cool to give a go.
Homework task.
Yep, so.
Cool.
You do?
Yes.
Okay, afterwards I'll dig out my stats for I didn't get Firefox completely starting up through QEMU, but at least in the startup we'll see how much was actually used, and we'll see if it works.
Okay, so this has been a fun aside, but we still need a static link so that we can do a static compare, right?
GNU libc is obviously not designed to be linked statically.
To put politely, yes.
Horrendous results.
Okay. So is there a static libc that we could use an alternative?
There is. And drum roll, Dart libc. So Dart libc is nice, it's cut down. A lot of the extraneous features of libc are pulled out. And it makes for quite small binaries.
Yep. Okay, so and it's really easy to use. You go cc equals diet cc, and away you go. And we run on our 3 binaries, and we end up here. So yes, it's bigger, obviously, than the, we're using OS here to compare. So this is with OS. We've already cut our 30%. And yeah, we get bigger because we're statically linked, but we're not insane anymore. So there's our diet libc, OS compiled, modern binaries. Okay, and this is the total. So yeah, we're actually looking at that. We've definitely won. Okay, so from now on, we're OS, diet libc.
Let's come back to the runtime coverage then. So these were the figures that we got from glibc in the previous experiment. So cat is pretty similar to our return 42. It doesn't do much, but it doesn't run much. With diet libc, not only have the binary sizes plummeted, so what, cat's 8 or so times smaller, but the usage has gone up a little bit as well. I like to think maybe this is more an efficient code path.
Yeah, and the total amount of instructions executed has obviously dropped. We're actually right back down to something that's a little bit more acceptable. But we're still not in the PDP-11 range.
So we're looking at a 16-bit machine, and we're comparing that to a 64-bit machine. So this is also something that's unfair. These are nice modern binaries.
This obviously is a 16-bit machine. Now, let's do a bit of an experiment. What if they had created a 64-bit variant of the PDP-11?
4 times the fun.
I imagine it would look something like this. There we go.
You can feel their relation.
Yeah. Now, I didn't go as far as actually to write an emulator for the PDP-44. or write a toolchain that will produce binaries, et cetera, et cetera. So I used an approximation. What I did is I took the assembler dumps of our 3 victim programs, and I looked at the text and I processed it. And I kind of said, well, this instruction is using one of those register offsets. You can say this register plus or minus a constant inside the instruction. Let's assume that adds, that we're going to, rather than being, plus or minus 15 bits, we're going to be plus or minus 39 bits, because some instructions would perhaps need more and some would need less. It can't really be plus 3 bytes because they all need to be word length. But that's sort of a compromise. Let's assume each branch, whereas it's plus, it's plus or minus 128, goes to plus or minus 2 to the 55, fairly common. We don't actually go for the whole instruction, you don't go for the whole 64-bit range, but we've got a fair branch range there. And just assume any literal becomes basically, goes from 16 bits to 32 bits, 32 bit in size. So we add 2 bytes to any literal in the instruction stream. Now for the data itself, I actually went through the C programs and I said, well, that would now be a pointer, that would now be an int, and scale it out accordingly by analysing our 3 programs source. And of course they pull in libraries, and I didn't actually do the analysis on the libraries, so I just scaled those numbers up, assuming that the same things would apply to the libraries. And then the padding. I assumed that we went for a 64-bit a.out header. It was 8 words before, it's 8 words now.
Didn't move to ELF yet.
No, we're definitely not in ELF territory yet. Okay, here are the results. We get a significant amount of text bloatage. We get a little bit of data bloatage, but not much. Mainly that's buffers. A 512-byte buffer is still a 512-byte buffer in 64-bit. If we do our totals, we can approximately say that we're paying a 50% bloat penalty because of 64-bit on my completely made-up architecture. So,
Well, okay, reasonable, but
yep.
Can we sanity check this? Can we compare it to anything else that's gone to a 64-bit architecture recently?
Well, yeah, I mean, we can take my 32-bit Ubuntu laptop and we can do the difference in sizes of the total, those 3 totals for the cat, grep, and ls. And yeah, that's actually only 9%. If we had a 16-bit Ubuntu, we'd be able to compare all the way. But saying 25% is certainly a reasonable ballpark from that. So I'm going to stand by my 50% number as being not completely insane. In practice, compilers are going to get better and they're going to do a better job of alleviating some of that. But I don't think 50% is a completely ridiculous number. So there's our second result. There's something else we can do. Yeah. I can take the old V6 commands and I can forward port them to a modern Ubuntu system. Well, cat, that's easy. I'd already written it in C, and of course I'd written it in C that was reasonably portable. Don't turn on warnings, but it compiles and runs. And you can actually see diet libc has won here, right? Not only has it not added this buffer that the C library on V6 added, that extra 500 bytes, but we've actually cut the text size from PDP-44. Unfortunately,
ELF.
Now blaming ELF is a little bit harsh. Yes, the ELF header is larger, but also we want to be able to mmap separately text and data. And in order to be able to do that on a modern system, the text and data have to be aligned to a page on disk. So on average, you're just going to be throwing away 2K, half a page.
Or 64K machines.
So yeah, 32K on a 64K machine, just to get that alignment so you can map it in. And unfortunately, that total makes it slightly worse than the PDP-44 version. But that's reasonably comparable. Forward porting grep, oh, okay. It already supported VC and N, and for a bonus, for the old timers, a -B, which shows you the block number in which the match was found, which is pretty cool.
Which foot of tape it's on.
Yeah, that's right. So, yeah, we need to munge the source a little bit. We're using a pre-K and RC, and even then, if you didn't declare something, you assumed it was an int. Well, if it really was a pointer, we now have to tell the compiler that. There are a few libc routines to do things that were pretty simple. Printf was basically untouched, except what used to be %L for logical, we would now call %U for unsigned. That didn't fare quite so well in the forward porting. It did definitely get bigger through that. But the real fun one was this, ls. ls already had 10 options. You could already type ls-lart and it would work, which is pretty cool. The structure in which it packed the information was, some things like using a char for the user ID and group ID, that wasn't going to work anymore. But the 14-byte file name limit, of course, is what really hits us. We're now up to 256 bytes, so the first part of that buffer really blows up. You didn't generally use headers in V6, you just declared the structures, layouts, the way the routines expected them to be, so you had to declare all your own struct. We didn't really have the file star thing, but you declared a struct buffered file usually that had the right layout, and you called printf and everything else. A whole heap of things. We've already have a qsort in the standard library, so that was straightforward. And we used to directly read the directories. We'd open it up and we'd read 16 bytes out, knowing the first 2 bytes were the inode and the next 14 were the name. So that was pretty cool.
You've got a typo there.
Yeah,
That's fine.
okay.
Struct lbuff, star last p.
No, this is actually the real code.
It compiles?
Yes, yes it does. You didn't actually need to put the equal sign in this last p end bit here, because initialization was just, didn't actually require that. But this is my favorite trick. It didn't use malloc to allocate. It uses sbreakoff_end. So your program's a certain size, it's got an end marker symbol at the end. And when you need more memory, you just lay it out immediately after your program and you tell sbreak when the last one is going to go past your last pointer, your current one's going to go, +1 is going to go past the last pointer, you just sbreak another 512 bytes.
Equals plus?
Yeah, equals plus, they're all backwards too, so we have to fix those. And this is cool. Our last p is actually a pointer, and it's of the same type, it's a struct lbuff star, the same as last p is. And we do .idev equals plus 512. You see, structure members didn't have a separate namespace. So you could do anything dot something, and it went, somewhere in the program there is a struct that has an idev member. So you know what you're doing. You're going to treat our last p as one of those structs. Now it happens that idev is the integer member, and it's the first member of the structure. So this is effectively saying, well, our last p offset 0, treat it as an int, and add 512. If they added 512 to the pointer, they would get 512 times by struct lbuff.
Dorothy, you're not in GCC anymore.
This confused the hell out of me when I first read it. And yes, that required some slight modification. So here is the result. This was harder to forward port because you can't just use the sbreak trick anymore. You can't just sbreak off end. Firstly, because glibc will malloc and use sbreak and allocate things even before you hit main. Secondly, these days you can't just open a directory and read it. You're supposed to use opendir. And opendir returns you a handle, which it is mallocked. So you really have to use realloc for your array. You mallocate it and then you reallocate it, which means you can no longer keep a single pointer to it or a couple of pointers into it. You need to take into account that the whole thing could move. So your code becomes significantly more complicated because of all this modern infrastructure that you have to use. This version in the end actually used the getDent system call, which has other issues that make it slightly different from read. But we get there, and it's significantly bigger. Now we can say 2 things from this. Firstly, we look at this bloat, and we can say with 20% of bloat, we are paying for elf and mmap, which is a roughly 20% penalty. But this is the big one. 120% penalty for modern infrastructure. Malloc, aka alloc in V6, was an optional extra that now got baked into our APIs, that for portability reasons became the way to read directories, and now you have to use malloc. You just can't do the sbreak thing anymore. Sbreak was awesome. You could qsort on that array, which is what they were doing. You can't do that anymore. And also, even if you do that, which is what I do, it's not actually very good because you could just read into these little elements. Now they're going to be quite big because file names could be up to 256 bytes long, even though 0.03% of the file names on my home system are actually longer than 63 bytes. But just in case, we went all the way out there, which makes it incredibly inefficient to code that way. You have to do something more sophisticated, like an array of pointers into a variable link structure, which now means you need 2 arrays that grow, which means, again, you can't use sbreak. You have to use a realloc and a real allocator and pull all that in. And this is the result.
Now, we've seen the old code. Next step is for us to backport all of the new utilities to V6 Unix.
I don't even know what that would mean on a teletype.
You have like a highlighter pen or something you can kind of...
Okay. How many options do you think GNU LS has today? Who says 10? 20? 30? My guess was 30 when I tried. 40? 50? 60? 70? More than 100?
Stop. How many have we got?
Okay. Okay.
Okay.
The answer is 60. So we did a survey of our hacker friends and said, here's all the options. Which ones do you use all the time? Which ones have you ever used? Which ones have you heard of? 11 options.
You might think. Yeah.
11 options, as far as we can tell, have never been used since they were implemented. That's the ones down here. Nobody knew existed. What's interesting is that of the ones that over half the people said they used all the time, all of them bar the -- color were all in the original LS.
Well, let's take this set, go back to our code coverage, have a look at how this changes. So 39% now instead of 23%.
Yep.
This is adding in all of the options anyone has ever used.
Yep. So not all of them, just all the ones that people actually use. So yeah, we do actually use some of that extra bloat that we've got.
61% maybe for those extra 11 really, really good options.
So I wasn't going to actually backport, but what I can do is actually cut out all the options that we didn't have. I didn't do grep, eno time, but cat and ls, and rip out all the features from the GNU ls that weren't in the V6 versions. For cat, it's easy. You remove every option and you remove all the error reporting. Done. It does stat the input and output buffers to get the block size to figure out the optimal size for its internal buffer to read and write. So I left that in because it's a modern optimization. It has to do with portability, and it's something you probably should be doing. It uses these generic read-write loops that everyone uses, so it's in lib and core utils. They handle eintra, even though we don't need to in cat, because we don't handle signals. What's fascinating is it mallocs this buffer, and it over-mallocs it by a page size -1, and then bumps the pointer up so it will be a beautifully page-aligned buffer, and I have no idea why. So I left that in. Because anything that mallocs as first thing in the program will actually look really good when we measure it on a naive size thing. I actually did change it to an 812 byte buffer to get some numbers out. And here's the result. This is the GNU static diet libc, and here's my reduced version. But here's the forward ported version. Interesting. So let's also look. Oh, yeah. You were looking through this.
I was. I found Russ had used abort instead of exit at one point. Abort's a sensible thing to do. Abort then added, what, 33% more?
Yeah, it was 30% larger because I just thrown in an abort there in one of the error cases.
Kill. It's got raise, you know. So there's a
Sig
whole load of extra
context raise.
stuff.
We pulled in all this stuff just because there's one line. Change it to exit 1,
So
and we drop.
that. Yeah.
There we go. 300 bytes. LS was a bit harder. We remove all the non-V6 options, we remove all the long options, we remove colorization, we remove interlateralizations, symlink, socket handling, blah, 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 blah. I kept. It does, as it goes through the LS, it figures out what width all the columns should be. Now I kept that because it is a consequence of the fact that our systems are so large that we need to do that. It used to be, yeah, one of the columns could be a bit distorted because you could have some particularly long, you could have a long size in there because it could be a bit bigger than the average. But now it could be a multi-terabyte file and everything will really be distorted. So I left that logic in there. It uses its own sort routine because they have one in lib and core utils. It does handle errors better. If you fail to stat, you actually print out question marks. I left that in.
I like this clock get time bit. So clock get time not only brings in librt, so extra dependencies, gives you the time in nanoseconds. Why does
LS need to know clock get time? Why does it need to know the current time? Anyone know?
So LSLTR works.
No, you don't care about the current time for LSLTR. It does it so that it can print the date string differently if it's more than 6 months old.
Yeah. To the nanosecond.
To the nanosecond. So performance.
Features.
So we do all this stuff and we looked at performance. And here is our forward ported LS and LS-L on the 500,000 directory entries. And here's our reduced versions. Now interestingly, even though we haven't used any options we haven't ripped out any of the options that these tests are using, we're still way faster than the straight GNU LS and GNU LS-L. Until I realized, of course, Ubuntu just decided that I don't want ASCII order. I want things to be collated and sorted in an order that, folds the cases. And this is the penalty that we're paying. LS is over twice as fast when you set lang equals C. So this should nominally be equivalent, but we're paying 20% overhead in time there just for features that we don't use. Okay. So here is our result for LS. And if we interpolate those results for grep and get a total, we look like this. So this is the difference between the forward ported versions and those reduced GNU versions. And we do actually pay 60% because of flexibility. Because we expect things to be portable, modern systems, we do a little bit more optimization and everything else. So we do pay a 60% penalty because the way you're expected to code in a modern world is different. We're portable, we're flexible, we have room to expand all this infrastructure, and that definitely paid. But this is the big one. We have 440% bloat because of all those features that we added. And that's where it's really coming from.
So very quickly, coverage.
Yep.
Okay.
This was before.
The originals.
This is the cut down versions.
So LS with the survey options. This is all the extra stuff that everyone in the lab around us had been using. The LS before, 65% to 66% at the bottom.
Yep.
Okay, so that 1% is, I don't know of any of those options. It's the cut down version, they're all taken out. So that's the error handling path and printing out the nice, I don't have any options error.
Otherwise they'd be identical. But yeah, you can see our density, execution density is actually stepped up pretty close to PDP 44. And there's the numbers. Okay, so in conclusion, I just don't think we could write, people are not prepared to write, to go to the extent to write today. Oh, yeah.
There are people that are prepared to go to that extent. There's a great ASM utils project. People have been implementing things that you'd find in /bin, in bare assembler, in NASM, not even GNU AS.
Yeah.
No libc involved. They've got all that stuff down. It's amazingly portable. It's x86, but it runs on FreeBSD as well as Linux. It's interesting.
32-bit.
They've got a fake header. The ELF header is 76 bytes. It's just enough to fool the kernel into loading and executing the thing. But all the bin utils just go, no, I'm not looking at that. So
getting stats for these was, yeah.
Very, very good. Cat's even got some options. So that 93%, that's less. It's got some actual other stuff that we didn't test. So
grep, 100% coverage. Well done.
It's got no regex. It just does strictmp. It doesn't actually do a regular expression.
So our real conclusion is here. This is the basic graph. And of course, if we pull out static glibc, which is progressing everything else, it looks like this. And for Matt, of course, it looks like this. There's ASM utils. Shocker. ASM utils, first thing it does, BSS is huge. All that stuff that you gain by having this tiny, tiny text, you lose again by having, by sucking up 32K for buffers and things like that. You're actually better off with forward ported or possibly the GNU reduced versions that actually have features and are actually implemented in C than you are with the ASM utils. Classic case of optimizing what you can measure. You can't run size in these binaries. I had to hack the kernel elf loader to tell me how much BSS it was using. And they obviously don't actually measure that. And so in fact, completely wasted effort as well as non-portable. Thanks, guys. For those of us who like random graphs that make things look pretty but actually make no sense, here is our pie chart showing percentage contribution for bloat. And as you can see, features are killing us.
The hook's coming out to drag us off stage.
Cool. Excellent. And we have no time for questions, but we will be hanging around in the foyer afterwards if you have any questions.